In this video, we're going to discuss probability. Probability is the chance an event will occur. What we're talking about is when we're looking at any type of action, any type of subject, what is the possible outcomes and what is their chance of occurring? And so we're going to look at several definitions to start off with. And one of them is going to be probability. Let me get this a little bit larger for us. So one of them is going to be probability experiment. And what that is going to be the chance process that leads to well-defined results called outcomes. These are just what anytime you're doing an experiment, things like that, that's what we're looking at here. Now then, for an actual outcome, this is something that we all want to see, and an outcome is the result of a single trial. So a result of a single trial of a probability experiment. And for an example here, we're going to look at a trial is flipping a coin once or rolling one die once. In other words, we've done it one time, and so that's an example of a trial. And so we want to look at what are the possible outcomes. Anytime that we have a trial or anything, we look at the outcomes. And so when we do, we set up what we consider as the sample space. The sample space is the set of all outcomes, or all possible outcomes, of a probability experiment. So let's look at what I'm talking about. And when I discuss that, what I mean is, like, if I have an experiment and I want to look at what its sample space is. Okay? So one experiment might be that we toss one coin. So think about, what is the sample space of tossing one coin? Well, tossing one coin, I can get either a head or I can get a tail. Therefore, my sample space is head or tail. The two of them together make up my full sample space. Another example is the roll of a die. A single die. What is the possible outcomes that we have? Well, on a die we have 1, 2, 3, 4, 5, and 6. I'm talking about a normal die, not a loaded die, not a 8-sided die or anything, but a normal 6-sided die. My possible outcomes are anything from 1 to 6. Okay, another possible example would be the answers to a true-false test or true-false question. What are the possible sample space? Well, think about what are the possible answers. Well, the possible answers are true and false. So that is my sample space. And I'm going to get into some other possible items and look at their sample spaces, but these are just some examples of this. Okay? One way of doing this is what we consider a tree diagram. So if we look at a tree diagram, this is going to be where we can, it's used to determine all the different or all the possible outcomes, determine all possible outcomes of a probability experiment. And it consists of line segments from one starting point to possible outcomes. So we're going to have one centralized area, and we're going to use that to start, and we're going to draw lines off of it, just like a tree. It's like branches off of a tree. So for example, if I give you use a tree diagram to find the sample space for the gender of two children in a family. Okay, so I want to use a tree diagram to find the sample space for the gender of two children in a family. So I'm going to start off here, and I'm going to have this set of branches, and this is going to represent the first child. Well, what are the possible outcomes for the first child? Well, the first child can be either a boy or a girl. From there, we do for the second child. So this is for the second child. And we do it off of each one of our first child branches. What are the possible outcomes for the second child? Well, it's still a boy or a girl. Boy or a girl. We wanted two children, so I have first child and second child, so I've got them. And then what I'm going to do is I'm going to follow my branches, and so my sample space is going to be a boy, boy. Let me try that again. So that will be a boy and a boy. It can be a boy, then a girl. It can be a girl, then a boy. Or it could be a girl and a girl. So my sample space for two children is boy, 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 girl, girl, boy, and girl, girl. So this is my sample space. And the order does matter in some of the times that we're discussing this. Not in all of them, but in some of them. And so it will depend on what we're discussing and how we're discussing it, whether we talk about does the order, like does it matter that it's boy, girl, or girl, boy, matter. We need to list all of those as possible outcomes because age can matter, things of that nature. Let's do another tree diagram. But this time, let's do one and say we want to use a tree diagram to find the sample space for the tossing of 2 coins. Well, we already know what the sample space is for tossing 1 coin. It's a heads and tails. Now let's look at what it will be for tossing 2 coins. Again, I'm going to start at one place and go off, and this will be my first coin. My possibilities were head or tail. Then off of that, for my second coin, I had a head or tail. Head or tail. So my sample space is going to be head head, head tail, tail head, or tail tail. Now if I wanted to do 3 coins, I would just keep drawing branches off of each one and continue the pattern. If it was something that had 3 possibilities or 4 possibilities, we could do a tree diagram even for that. We also want to discuss an event. An event is the set of outcomes. Yep, It's the set of outcomes. So, do we have one possible outcome? Do we have more than one possible outcome? Things of that nature. So, having one child is a single event. Having multiple children is what we're going to call compound events. So, a single event, also known as a simple event. That is an event with one outcome. In other words, we're only going to have the first outcome and that's it. A compound event is an event with 2 or more outcomes or 2 or more simple events. So 2 or more outcomes. So this is where we're going to have 2 children roll 2 die, roll 3 die, things like that. They're compounded onto each other. Now when we talk about probability, there's a couple of different types of probability that we're going to look at. And the first type is called classical probability. Classical probability. This one is going to assume that all outcomes are equally likely. Which does happen in a lot of ways. And in classical probability, you do not actually have to perform the experiment. have to perform the, oh boy, my pen's messing up again. Perform the experiment. Meaning we don't actually have to go out and do whatever we're talking about. When I discuss equally likely, that just means that they have the same probability of occurring. So talk about flipping a coin. You can either get a head or a tail. Therefore, how many chances do you have of getting a head? Well, it's 1 out of 2 because there's 2 possibilities. So if we look at flipping a coin, I don't have to actually go out and flip coins to find out that the probability of getting a head and let's try this again. So the probability of a head is going to be, there's 1 head out of 2 possible outcomes. The probability of getting a tail is also 1 out of 2. That's also what makes them equally likely. It's 1/2 and 1/2. The probability of getting a head is the same as getting a tail. So it's not going to change. We have a formula for when we're talking about classical probability, and that is that the probability is equal to the number of outcomes in E, which is going to be our event, divided by the total number of outcomes in your sample space. Just like I did here with the flipping of the coin, there was 1 head and there were 2 events in the possible outcomes in the sample space. There was 1 tail and there were 2 possible outcomes in the sample space. We normally write this shorthanded, just like all mathematicians, and we say the probability of whatever our event is equal to the number of that event divided by the number in the sample space. So let me come over here. E is equal to, represents event. So that's what we're looking at. What is the event that we're talking about? And usually that's getting a head, getting a 2 on a die, things of that nature. What are we trying to get when we're looking at that? P of E, you'll see this type of notation quite often. That's the probability of event E happening. So this is the probability of event E. N of E is just equal to the number of outcomes. Let me try that again. So the number of outcomes in E. In other words, is it 1, is it 2, is it 3? And as we go through, we will be looking at several of these. And then we also have N of S, which is the number of outcomes in the sample space. So in the sample space. And I cannot spell for some reason. Let me try that again. Sample space. Okay. So S represents your sample space, and E represents whatever the event, whatever outcome you're wanting to happen. A couple of rules that we want to make sure that we know, and that is probabilities, and since I want to make this plural, these can be expressed as fractions, decimals, or percents. You have to be a little bit careful if you're expressing them as fractions. It needs to be in simplified form, and when you're expressing them as decimals and percentages, normally you make sure, okay, how far out do we want to go? We want to go out usually as much as possible, but how far's that? Usually we round to 3 decimals. And again, simplify all fractions. So make sure that you simplify your fraction. And my M is not coming up very well there. So simplify your fractions. Again, you can write them as fractions, decimals, percents. Just make sure that you simplify them completely. Okay? Now then, let's look at an example. And for this, I'm going to try and type it. So, example, I want a card is drawn from an ordinary deck. When we're talking about an ordinary deck, we're talking about an ordinary deck of playing cards, ace through king of all 4 suits, jokers taken out. We want to find the probability of getting an ace when we draw this card. Okay? So a couple of things have to happen, and one of those is we have to know how many cards are in that deck. So one thing to know about a deck of cards is there are clubs, and let me write these in the color that they should be. So there's clubs, there are spades, there are diamonds, and there are hearts. These are the 4 different suits of cards. Then of those, we have, that didn't go over well. Let me try that again. That's a little bit better. Okay. So, of the clubs, we have an ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, King, Jack, Queen, and King. Of the spades, we have the same thing. I have 6, 7, 8, 9, 10, Jack, Queen, King. And of the diamonds, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King. And of the hearts also. Okay, so here's what the deck of cards kind of looks like. And if you'll notice that I have 2 rows that are black, clubs and spades are both black, diamonds and hearts are both red. I have a total of 52 cards in a deck of cards. There are 4 aces, 2 red, 2 black, 4 twos, 4 threes, 4 fours, so forth. These right here are the ones that are considered the face cards. So if anytime you're looking for a face card, you're looking for the Jack, Queen, or King. So if you notice, there are a total of 13 clubs, 13 spades, 13 diamonds, and 13 hearts, which adds up to 52, which also gives me a total of 26 black and 26 red cards. Now that we see the basics of our cards, we can go back and look at the probability of finding an ace, or drawing an ace. So the probability of drawing an ace, well, we know that there's a total of 52 cards in the deck. How many aces are there? Well, if I look at my deck of cards, there's 1, 2, 3, 4. So there's 4 aces. So it's 4 out of 52. I simplify that. I can either, again, write it as a fraction, 1 out of 13, or I can write it as a decimal, rounded to 3 decimal places. Or I can write it as a percentage, 7.7%. Most of the time, one of these two, where it's asking for probability. I only put it in percentage form if it's asking for a percent. If it's asking for a probability, I still leave it in fraction or decimal form. Okay, so let's look at another example. Similar to this, now that we know the basics of our cards. And see what we can do. Let's see here. If I say a card is drawn from an ordinary deck, find the probability of getting a face card. Well, if you recall, I told you that, let's look back up here, Jack, Queen, and King are considered face cards. So whenever I go to solve this, I'm first going to write the notation correctly, probability of a face card. I have a total of 52 cards. And then if I think about it, I've got 1, 2, 3 for each suit. So 3, and there's 4 suits, so that gives me 12 cards. Oh boy. So that's 12 out of 52. which is going to simplify into 3 out of 13, which is also the same thing as 0.23077, which if I round that to 3 decimal places, that's going to be 0.231. I can either leave it as 3 out of 13 or 0.231. And these are ways of doing classical probability, which is what we tend to do most of the time in what we're looking at. Now what we want to do is we want to look at some probability rules. So let's look at some probability rules. And first one is that probability must be between 0 and 1. Therefore, it can equal 0 and it can equal 1. But it's going to look like this, which means I can equal 0, I can equal 1, but I have to be between those. I'm not going to have any negative numbers, and I'm not going to be over 1. Okay? Then I also have that the sum of probabilities of all outcomes in a sample space is 1. So if I take the probability of getting ahead on flipping a coin, that's 1/2. And if I take that and add it to the probability of getting a tail, which is the other item in the sample space, which is 1/2, and I add those together, I should get 1, which I do. So the probability of all the outcomes have to add up to 1. If an event cannot not occur, then its probability is 0, meaning not a possible chance. So think about when we're talking about drawing a deck of cards. Okay, what's the probability of drawing a 14? Well, there's not a 14 on the deck of cards, so the probability is a 0. Rolling a normal die with an outcome space of 1, 2, 3, 4, 5, 6, what's the probability of rolling an 8? It's not possible, so the probability is 0. If an event is certain to happen, or certain to occur, its probability is 1. Therefore, okay, something must occur, something is going to occur no matter what, then it's going to have a probability of 1. We have very few of them that are probabilities of 1, but it is possible. When we're talking about probability, we also need to discuss what we consider the complement of an event. This is the outcomes in a sample space not included in whatever event we're looking at. So this is the set of outcomes. Set of outcomes in the sample space. That are not included. Let me underline that, not included. In the outcomes of event E. Okay. We denote this by an E with a bar over it, and that's how we pronounce it, E bar, or not E. Okay. So for example, if I have E as being the sample space of getting ahead, not E would be getting a tail, because getting a tail is not in if I'm flipping a coin. And so because it's not included in event E. So it's everything outside of event E. So if I'm rolling a die and I say event E is the even numbers, which would be 2, 4, so 2, 4, and 6, then the complement of that would be the odd numbers, which is 1, 3, and 5. So it's everything that's not included in our original E, or our original event that we're talking about. We always have some rules that go along with it. So rules for complement events. And the first one is that the probability of E bar is equal to 1 minus the probability of E. So that means that the probability of E and the probability of E bar have to add up to 1. Remember, everything, the sum of the probabilities of all outcomes in our sample space must be 1. So, and where we're talking about complementary events, it's either got to be an E or it's got to be a not E. Okay, so it's got to be in one or the other. So whenever we add these up, it's got to be here. I can rewrite this one to say that also the probability of event E is 1 minus the probability of E bar. So whichever one that I do have, whether I have E or I have E bar, I can take 1 minus it and get the other one. Okay? These are going to come in extremely handy as we go throughout the rest of our probabilities. So this is regarding classical probability. Complementary probabilities come up with just about everything. Another type of probability that we're going to look at is empirical probability. This relies on actual experience. And what we mean by that is we rely on this to determine likelihood of outcomes. So what we're talking about is based on what we already know, what is the likelihood of this? What is the likelihood of something going to happen? We've already done some experiments, or we already know something's going to happen, or most of the time this is when we are given a frequency distribution, because we can look at the frequency of something. So when we're given a frequency distribution, the probability of one class or probability of an event, let me write it this way, of an event in one class is going to be probability of event E is equal to the frequency of the class. So the frequency of the class divided by the total frequencies. And I'm having trouble with my pen again. My total frequencies. Okay. Shorthandedly, the probability of event E is equal to our F divided by our N. Remember, our N is our total number that we're looking at. This is also a lot of times called relative frequency probability. So, because when you find relative frequency, it's the exact same thing as this formula right here. So a lot of times we can do the relative frequency probability. The third type of probability that we discuss is going to be subjective probability. Subjective probability, and this is based on an educated guess. This is how we can estimate things, and it also employs opinions. Empirical probability, we use it for a lot of polls, things of that nature. Subjective probability is used a lot with forecasting. There's a 20% chance it's going to rain. We don't know if it's going to rain or not, but based on the computer models, things of that nature, and everything, the forecasters and everybody, meteorologists, are going to say there's a 20% chance that it'll rain. And they're right part of the time. Part of the time, they don't know. They put an estimation on it. And that is a type of subjective probability. We're going to focus mostly on classical probability and a little bit on the empirical probability. We don't do much subjective probability in here because we do not have enough of the educated guess or the education to guess at a lot of things. You do that if you're going on into psychology, things of that nature. Even in medicine, okay, you've got these symptoms, it's most likely going to be this disease. It's still an educated guess sometimes unless we have an actual test that we can run for it. But again, we're going to focus on the other two, mainly classical probability. If you have questions, please let me know.